5 minutes to understand how multiple robots work together to explore planetary lava tubes. From Apollo 11's first moon landing in 1969 to Elon Musk dreaming of sending humans to Mars, this paper in Science Robotics shows that robotic exploration on other planets isn't as far off as you might think. You're probably only going to get a breakdown this detailed here on 5-minute robots. So don't forget to like and subscribe. Over the past few decades, humans have mostly explored the surfaces of other planets, but we still know very little about what lies beneath, especially the inside of lava tubes. Yet these lava tubes could be incredibly valuable, both scientifically and for engineering. On one hand, the cave interiors are relatively stable and protected, and they might even hide signs of life, which is super important for astrobiology. On the other hand, lava naturally shields against radiation, temperature swings, and micrometeorite impacts, making these caves ideal spots for future outposts on the Moon or Mars. But cave entrances are often steep, the environments are tricky, and communication is limited, so sending humans in directly is extremely risky. Even a single robot has clear limitations in reliability, adapting to the environment, and covering enough ground. To tackle this challenge, the research team proposed and tested a complete framework for multi-robot exploration of planetary lava tubes. They built a collaborative system composed of 3 heterogeneous robots, each taking on a core task at different stages. First, there's the Sherpa TT, which excels at surface exploration and can provide mechanical support as a mobile anchor. Then we have the LoveMe X, capable of mapping the surface and deploying sensor modules. Finally, the Coyote 3 is small, highly maneuverable, and perfect for venturing inside the caves. By complementing each other's strengths, these 3 robots work together seamlessly, from sensing the environment outside the cave entrance, to capturing the cave's internal structure, and finally, to exploring deep inside. To validate this approach, the research team designed 4 consecutive, connected mission stages. At the start, the 2 surface robots first autonomously survey the area outside the cave entrance, building a digital terrain model and creating a high-precision, collaborative digital elevation map. At the same time, the small rover uses ground-penetrating radar to try to detect the underground cave structure. Next, the team introduced a breakthrough technique, using deployable sensor cubes to explore the interior of the cave. These devices are equipped with multimodal vision and depth sensing tools, allowing them to build a real-time 3D model of the cave's interior as they descend. The data is then sent back to the surface robots, where it's analyzed to precisely locate the narrowest skylights and identify the safest entry points with the gentlest slopes. After fully understanding the cave entrance structure, the exploration system moved into the most critical phase, descending into the cave. The research team designed a tether management and docking system, using Sherpa TT's robotic arm as a mobile anchor to control a safe, controlled descent of the Coyote 3 via rope. During the descent, the system could adjust to the rope tension and descent speed in real time, keeping the robot's posture stable and preventing overload on the robotic arm, ultimately allowing Coyote 3 to reach the cave floor safely. Once detached from the tether, Coyote 3 immediately began its exploration mission inside the cave. Despite the complex and ever-changing environment, with rocks, slopes, and rough lava terrain, the small rover successfully traveled long distances and collected 3D structural data of the cave interior. It's worth emphasizing that this wasn't just a simple lab simulation. The mission was carried out in real volcanic lava tubes on Lanzarote Island, Spain, providing a highly realistic and representative analog for extraterrestrial environments. The experiment successfully demonstrated the full end-to-end exploration process, from the surface to deep inside the cave, and confirmed that the multi-robot collaboration approach is both reliable and practical. The core innovations of the paper are highlighted in 2 main aspects. First, this is the first time a complete and executable framework for collaborative planetary lava tube exploration has been proposed and implemented, covering the full mission chain from sensing outside the cave entrance to exploring deep inside. In particular, the multi-robot role division and collaboration mechanism offer a new solution to the limitations of a single robot's capabilities. Second, the paper introduces a technical innovation that combines low-risk cave entrance sensing with safe tethered descent into the cave. By using deployable sensor cubes and controlled rope descent, the approach effectively reduces the risks of cave exploration, ensuring both safe entry and accurate 3D modeling. Overall, this study not only provides a practical, implementable solution for planetary cave exploration, but also lays the technological foundation for future extraterrestrial outposts and the search for signs of underground life. If you enjoyed this, don't forget to like and subscribe so you won't miss more amazing robotics.